you can always write down your questions on a piece of paper and hand them to me, and I can always ask for you. Okay, so I'm very excited to introduce our speaker today, Dr. Ninareh Mehrabi. Nina is a postdoctoral scientist at Amazon's Trustworthy Alexa AI team. She received her BSc degree in computer science and engineering from the University of Southern California and completed her PhD in computer science at the University of Southern California's Information Sciences Institute. She's a recipient of the 2021 to 2022 Amazon Fellowship from USC Amazon Center on Secure and Trusted Machine Learning. Her research is on developing trustworthy AI systems with an emphasis on algorithmic fairness in machine learning and natural language processing. And I'll let her tell you more about this.
Hello, everyone. Thank you so much for the introduction and having me today. So today I'm going to be talking about some of the work I have done towards developing trustworthy AI systems. So as you already know, machine learning and AI systems are being utilized in various environments, and some of them are even sensitive environments, such as loan allocation systems. And it's important for these systems to be fair and not discriminate against some people or demographic groups. AI systems are being also incorporated in autonomous vehicle systems, and it's important for these systems to be robust. As well as we utilized AI in healthcare, and it's desirable for these systems to be interpretable. So overall, we need AI systems that are trustworthy for us to be able to reliably trust these systems. However, we see so many headlines and news articles on types of issues that might arise in these systems. So we see cases such as AI systems discriminate against people of color, let's say in medical algorithms. We also see some robustness issues, as well as some dialogue systems generating unsafe responses, and so many other issues. So then the most important question becomes the following: how can we design trustworthy AI system so that we can reliably trust on these systems and use them? And here is what my presentation is gonna focus on. So first, I'm gonna introduce what a trustworthy AI system is and its components. Then I'm gonna talk about the first main component of trust, namely fairness, and talk about work we have done on investigating representational harms or biases in common sense reasoning tasks and resources. Then I'm gonna move to the second component, namely robustness, and talk about robustness of machine learning systems to data poisoning attacks. And lastly, interpretability, and how can we design algorithms that are fair as well as interpretable. And lastly, I'm going to talk about some conclusion and remarks, and we'll end the discussion as such. So let's start with some introduction about trustworthy AI. So a trustworthy AI system is a system that is robust, fair, and interpretable. Of course, there are other components that contribute to design of trustworthy AI system, but for the sake of this presentation, I'm gonna just focus on these three main components. So we need AI systems that are robust against adversarial attacks that can trigger privacy, security, safety, and fairness issues. We also want our AI systems to stay away from any favoritism or prejudice towards different individuals or demographic groups. And lastly, we want to be able to understand how AI makes decisions, which can be beneficial to other components of trust, namely accountability. So let's start with the work on fairness. So in this work, the goal was to investigate representational harms or biases in common sense knowledge, resources, and tasks. So to start this work, I'm gonna first describe what a common sense knowledge is. Common sense knowledge is facts about the world that all humans are expected to know about. So based on this definition, common sense knowledge should be facts and not stereotypes or biases in terms of favoritism or prejudice. So the following example, a fish is capable of swimming, is a form of common sense knowledge because it's just representing fact about the world, and we are expecting all humans to know it, and there is no stereotyping or bias in terms of favoritism or prejudice towards any individual or a demographic group. However, we have some undesirable cases, such as a politician is capable of telling lies. So you might ask me, okay, politician is a human is capable of telling lies. So this is a fact that is represented in a knowledge base. That is correct. But the problem is when we just associate liars to politicians and not other occupations, and indeed we might represent doctors to be trustworthy versus politicians liars, etc. So this is where the problem is coming from. So the AI system starts to learn such stereotypical views or biases to associate to certain people or demographic groups. So in this work, we wanted to study and quantify harms in common sense knowledge resources. And more specifically, we studied two knowledge bases, namely ConceptNet and Generics KB. And then we studied two downstream models that are trained over ConceptNet, namely common sense knowledge generation and completion and common sense story generation. And lastly, we propose a mitigation framework by pre-processing technique that is basically filtering the bad data. So before starting talking more in detail about this work, I'm going to first describe different types of harms that can exist in our systems. So on one hand, we have allocation harms, and these are when a system withholds certain groups some resources or opportunities. So for instance, in loan allocation systems, if the system discriminates one group over another by allocating loan to one group versus another, we say that this system is suffering from allocation harm because it's withholding some resources from some certain groups. So a characteristic of allocation harm is that it is easier to quantify. So we have so many measures nowadays for fairness, like statistical parity, equality of opportunity, etc. And these are mostly designed to capture allocation harms and differences on how resources are being distributed. On the other hand, we have representational harms, and these are harms to the identity of certain groups, making them appear inferior regardless of allocating them resources or opportunities. So in the example that I just discussed about associating liars to politicians, this is a type of representational harm because we are representing certain groups in a way that is not desirable. A characteristic of representational harm is that it is difficult to formalize. And this is exactly what the focus of this portion of the presentation is gonna be on more specifically the representational harms in common sense knowledge, resources, and tasks. So we first define what we mean by bias or harm in this work. So we define bias as the existence of prejudice or favoritism toward an individual or a group based on their identity. And then we come up with different types of representational harm. So we describe the concept of overgeneralization, which is if there exists prejudice or favoritism toward individuals or groups. So basically, if we are studying one group in the knowledge base, we are interested in seeing how are we representing this particular group? Are we favoring this group in a way we are describing it in the knowledge base? Are we disfavoring this group? Or are we just representing this group in a neutral way, which is what is desirable because these knowledge bases are supposed to just represent facts about the world. Then we introduce the concept of disparity in overgeneralization, which means how different individuals or groups are represented in terms of overgeneralization harm. Meaning if you are studying different groups in our knowledge base, let's say 3 groups, what are the disparities in how we represent each group? For instance, if we are favoring the first group in the way we are representing, disfavoring the second group, and being neutral to the third, there is obviously disparity in how we represent each group. So we call this disparity in overgeneralization. And lastly, we have the concept of disparity in frequency, which is basically saying, is the knowledge in the knowledge base sufficiently representing an individual or a group? So again, in the same example, if we have tons of knowledge representing one group over just few for another, there is obviously disparity in the amount of information present in the knowledge base to describe a particular group. So then the question becomes, how are we going to quantify these concepts? So the knowledge represented in the knowledge base is in the form of triples, let's say in the concept net. And here is an example. Let's say American is a citizen of America. What we do is we convert this triple to natural language sentence, and then we apply sentiment and regard classifier to obtain sentiment and regard labels that are going to serve us as proxies to bias. So basically, sentiment is a classifier that gives us the label representing the sentiment associated to a sentence. So if we get a positive sentiment label, we say that we are observing favoritism for this particular sentence according to sentiment classifier. And regard is a similar classifier to sentiment, but it's specifically trained to capture stereotypes or biases in sentences. So again, we use the labels obtained from regard classifier as proxies to bias, meaning if we obtain positive label, we associate it to favoritism, negative to prejudice, and neutral labels is the ideal case. So then we formalize these concepts as follows. For overgeneralization, we report the percentage of positive or negative sentiment and regard labels over all the sentences for that target group. So basically, let's say if we are studying teachers as a demographic group, if we have 10 sentences representing teachers, out of these 10, 5 of them have a positive label. We say that according to sentiment, the amount of positive overgeneralization is 50%. For disparity in overgeneralization, we report the variance in these positive, negative overgeneralization percentages among different target groups that we studied. And for disparity in frequency, again, we report the variance in frequency or the existing concepts in the knowledge base amongst, again, different target groups. So we studied more than 300 target groups from 4 different categories, namely origin, profession, gender, and religion. From the origin category, we have cases such as American, British, and other nationalities and origins. For profession, we have different occupations such as nurse, psychologist, etc. For gender, we have some gender-related words such as man, woman. And for religion, we have some religions such as Muslim, Christian, etc. Then to see whether sentiment and regard are good proxies for bias and harm, we do human evaluations. So we labeled 3,000 instances from ConceptNet and more than 1,500 from generics KB on Amazon Mechanical Turk with regards to if there exists favoritism, prejudice, or just a neutral fact. And we observed that human labels are in reliable agreement with these sentiment and regard labels, which shows us that sentiment and regard labels can serve us as reliable proxies to capture biases. We also compare labels obtained from regard and sentiment to a keyword-based approach. So basically, we curate a keyword or a dictionary of all those words that we associate to favoritism versus prejudice. And if a sentence contains that word, we mark it as positive or negative or neutral. And we observe that still sentiment and regard are better approaches than such a keyword-based approach. From our results, we observed that both overgeneralization and disparity in overgeneralization exist in both of the knowledge resources, and the degree is more severe in generics KB compared to ConceptNet. So in the plots that you can see in the bottom of the screen, we see the differences between ConceptNet and generics KB with regards to regard classifier or sentiment. And you can see the spread of boxes and the existence of some outliers, which shows us that there exists overgeneralization as well as disparity in overgeneralization. And we also show some qualitative results on top for the profession category, let's say. You can see some occupations such as mathematician or hairdresser are in the negligible bias region, which is the desirable case. We are just representing facts about these people. But you can see some cases such as politician lie in the red region, which is showing we are not representing these groups in an ideal way. And some cases such as CEO are in the positive or favoritism region, and some other occupations somewhere in between. And you can see from the spread of these occupations, the amount of disparity in overgeneralization for the case of profession category. Then we study two downstream models or tasks that are trained over ConceptNet. The first downstream task or model is COMET. COMET is a knowledge completion and generation model. It's trained on GPT and then post-trained on ConceptNet. We input the same target words that we used in studying ConceptNet as prompts and collect triples by following all the relations that exist in COMET. And we obtain 112 case statements that we perform the analysis over. The second task or model is common sense story generation, which given a prompt, the model will generate 3 to 5 sentences to tell a story. It extends GPT-2, then it's post-trained on common sense knowledge constructed from ConceptNet and Atomic, and it's further post-trained on ROC storage corpus to have a story format. We manually created 30 templates. We populated these templates with the target groups that we studied, and we obtained 3K prompts. And after generating stories, we obtained 12K sentences because each story contains 3 to 5 sentences. And again, we performed the analysis same way we did for COMET as well as ConceptNet. In our results, we observed both overgeneralization and disparity in overgeneralization in both of these downstream tasks, as you can see in the plots. And not only overgeneralization and disparity in overgeneralization is propagated from these upstream data resources to downstream models, but bias is even amplified. So if you remember, for COMET, we had around 30% in some cases. For COMET, we see spread to until 50%, and for story generation to 60%. So we see that not only bias is propagated, but it's even amplified in these downstream models. Then we propose a mitigation framework. Basically, the idea is to take the data coming from these knowledge bases, use the proxies that we introduce, namely regard and sentiment, and filter all the data that according to regard and sentiment are problematic. So what we do is we take the data or sentences coming from ConceptNet, we apply regard and sentiment classifiers on each of these sentences, and we remove cases that are associated to positive or negative labels and only pick the ones that are neutral. So after filtering this data, we then train our downstream model, in this case, COMET. Then we perform evaluation, human evaluations on Amazon Mechanical Turk, and we label 3,000 triples, comparing the original COMET to COMET that is filtered, basically the approach that I just described. Based on either bias exists in the form of favoritism or prejudice, and the validity of the generated common sense knowledge. We still want the model to generate valid common sense knowledge, and we don't want to degrade the performance. In our results, we show that indeed this filtering approach can be better in terms of reducing bias, but we are losing quality compared to the original comments. So there is a trade-off between achieving more fair outcome versus performance. And because we are filtering some of the data, this is the issue that some of the concepts end up not having good quality. So future work can be to how to design better models that are not suffering from this trade-off between fairness and performance. So that was all about the work on analyzing fairness in common sense knowledge, resources, and tasks. So now I'm gonna move to the second component, namely robustness. So I'm sure most of you already are familiar with the work done in adversarial machine learning. And as you already know, adversaries and malicious users can target machine learning models and cause serious safety and security related issues. So the field of adversarial machine learning arose as a result of these observations with hopes of proposing attacks and defenses to prevent harmful consequences. So adversarial attacks can fall under different categories. On one hand, we have evasion attacks, and these are types of attacks that happen during test time. And the goal of the adversary is to provide test instances to a benign model that can fool the model. So the example that is shown in this picture is an example of an evasion attack in which an adversary can take an image of a pig, perturb this image, and create a new image in which the model can mistag this pig image as an airliner. So this is an example of an evasion attack. On the other hand, we have data poisoning attacks, and these are attacks that happen during the train process, and the goal is to train a malicious model via some poison data instances. So as you can see, there is differences between evasion attacks and data poisoning attacks. Evasion attacks happen during test time, and the goal of the adversary is to trick a benign model that is trained in a normal fashion and just come up with adversarial test instances that can fool the model. But for data poisoning attack, these attacks happen during train process, and the goal is to create a malfunction model via injection of some poison instances. So the focus of this portion of the talk is gonna be on data poisoning attacks. So as I mentioned before, the goal of the adversary is to add, remove, or place poison data points during the train process that will result a malfunction model. And here in the picture, we show how a data poisoning attack works. So on the left-hand side, we have a model that is trained only on clean data points, DC. And as you can see, the model is doing a good job in separating red from blue points. But on the right-hand side, you can see that the adversary can inject poison points marked here as DP and skew the decision boundary and create a malicious function that is no longer able to separate red from blue points. And here is the objective of data poisoning attack. So we have the adversary that has a specific loss function and is trying to maximize it via these poison data points, DP. The size of DP or poison data points is proportional to size of DC, clean data points, and this proportion is controlled by the epsilon parameter. Then DP should also be a subset of a feasible set so that even if the defender runs anomaly detection, it cannot tell apart DP from DC. And lastly, we have the defender that has its own loss function and is trying to minimize it over all the instances, including DP. And as I mentioned before, because we assume that DP is gonna be a subset of the feasible set, the defender wouldn't be able to tell apart DC from DP, so it will just minimize its loss over all the instances. So most of the previous works on poisoning attacks attack accuracy as a performance metric only. We argue that fairness measures are as important as accuracy and can be attacked by the adversaries. For instance, adversaries can attack a system with regards to fairness to skew and bias decisions in their favor or in favor of a specific group in general. For instance, in loan allocation systems, adversary might want to train a model that always favors one group over another in allocating loan. Or a similar case can be in college admission, wherein adversary wants to create a malicious model that always admits certain groups from certain demographic group. Adversaries can also attack government agencies and degrade their values and credibility to make them appear discriminatory. So there are still safety and security concerns with regards to fairness metrics in adversarial setting. So we propose two sets of data poisoning attacks, anchoring attack and influence attack on fairness. In anchoring attack, the goal is to skew the decision boundary by placement of poison instances in the region. And we also introduced two types of anchoring attack, random and non-random. In random anchoring attack, target points are chosen randomly. And in non-random anchoring attack, target points are chosen based on their popularity, meaning if they're near to more similar instances to themselves. I'm going to explain each of these attacks in more detail, but this is just a high-level overview. And in influence attack on fairness, the goal is to propose a loss function, maximizing which can cause harm to fairness. So in anchoring attack, the goal again was to put poison points in space such that we can skew the decision boundary and create models that can be discriminatory. So what we do first is we pick initial target points from each of the demographic groups. So for instance, from the advantage demographic group, we pick a point that has label -1 and cloud it with poison points that are also advantage but have label +1. And this is done to skew the decision boundary and make more instances that were advantaged, but we're supposed to get the negative outcome to get the positive outcome. So we are, in a sense, making more advantaged people to get advantaged. And similarly, from the disadvantaged group, we pick initial target points that have label +1 and cloud it with poison points that are also disadvantaged, but have label -1. And again, this is done so that more disadvantaged people who were supposed to get the positive outcome end up getting the negative outcome. And this is similar to making the rich to become richer and poor to become poorer. And we are kind of, excuse me, skewing the decision boundary. Sorry. So the second attack is called influence attack on fairness. And the goal is to propose a loss function based on the decision boundary fairness measure, maximizing which using the influence attack will cause harm to fairness. Sorry. And in this work, this loss is composed of two parts. The first part is responsible for controlling accuracy. And the second part is responsible for harming fairness. And this harming fairness is based on the decision boundary fairness measure, which basically is trying to maximize the covariance between sensitive features and sign distance of the features to the decision boundary. So if you remember the objective of data poisoning attack, we had a loss function for the adversary that we were trying to maximize it. Here, this loss is going to be composed of two parts, L of accuracy and L of fairness. And again, the goal is to maximize this L of fairness and cause more harm to fairness. And we have this lambda parameter that controls this accuracy fairness trade-off. So basically, if we increase the lambda, we are assuming that we are going to cause more harm to fairness. So notice the differences between anchoring attack and influence attack on fairness. In anchoring attack, we are not directly touching this optimization function. We are basically just putting poison points in the region such that the decision boundary is skewed. But in influence attack on fairness, we are specifically solving this optimization and coming up with an objective for the adversary such that if we maximize this loss, we are going to cause harm to fairness. So then we perform experiments. For the baselines, we compare our attack to basic influence attack on accuracy. And this attack is merely targeting accuracy, so it's optimized to target accuracy only and not fairness. And the goal that we include this type of attack is to show that attacks optimized for accuracy cannot target fairness measures. And this is why we need specific attacks that are optimized for fairness only. It can also serve us as a good baseline to compare the performance of our attacks with regards to accuracy only. For the second baseline, we have another baseline, an attack that is specifically optimized to target fairness measures. So it's a good baseline to compare our attacks against this one, because similar to our attacks, this attack is targeting fairness only. For the measures, aside from accuracy, we consider two widely known fairness measures, namely statistical parity difference and equality of opportunity difference. From our results, we show that the influence attack on accuracy is not effective in affecting fairness measures, while it affects accuracy the strongest, which is what we expect, because these attacks are just optimized to target accuracy. So we expect these attacks to attack accuracy the strongest, but they are not working well to target fairness measures. We then show that the influence attack on fairness is the strongest attack that can target fairness amongst all the attacks, and that anchoring attack is still less subtle in harming accuracy as well as fairness measures compared to influence attack on fairness. But still, it overperforms the baseline that was specifically optimized for fairness. So two of our attacks are outperforming, but influence attack on fairness is the strongest in attacking fairness. But attacks optimized for accuracy are the strongest in attacking accuracy. So now I'm gonna move to the last component, namely interpretability. And the goal of this work was to design algorithms or models such that we know exactly what is happening. They are interpretable. So if we have a biased outcome, we want to know what features are contributing to this biased outcome. And moreover, how can we create more fair algorithms in an interpretable fashion so that we exactly know what features are manipulated by how much to get the fair outcome. So this is important because machine learning models are used in sensitive environments such as healthcare and parole decision-making systems. So it's important to assure both fairness as well as interpretability. So why is interpretability important? Because if a model makes a certain decision, we want to be able to explain how the model makes this decision. And we also want interpretable fairness, which means what features are contributing to unfairness, so we need to know that, and moreover, how can we design more fair algorithms in an interpretable fashion? This is important, again, because these decisions need to be audited, understood, and defended in these systems that are being utilized in sensitive environments. So in order to have an interpretable neural model, we first propose a general classification model that utilizes attention mechanism. We then use this model in an attribution framework that intervenes the attention weights to reason about the importance of each feature on the outcome. And to achieve fairness in an interpretable fashion, we use this attribution framework and design a post-processing bias mitigation strategy by diminishing the effects of the problematic features that we discovered in our attribution framework. So here is the approach outline. I'm going to first talk about the general classification model, then the attribution framework that tries to reason about the importance of each feature on the outcome. And lastly, the bias mitigation strategy that is giving us more interpretable bias mitigation algorithm. So here is the classification model. So we treat feature values as words are in sentences, and we learn an embedding for each of these feature values. We then pass these embeddings to the attention layer, learn a representation, pass it to the dense layers, and get our output. So this is how our classification model works, highly inspired by how classification is done in natural language processing. Then to reason about the importance of each feature on the fairness of the outcome, we first use the general classification model and learn the attention weights, similar to how I described using the general classification model, and use our primary output marked here as odd. Then to reason about the importance of the Kate feature, we zero out the attention weights corresponding to the Kate feature and get a secondary output marked here as odd prime. Then we calculate fairness accuracy differences between odd and odd prime. So what we do is, if we see that fairness measures such as statistical parity is becoming improving, we know that this feature was problematic, because if we are removing the effect of this feature, we are getting more fair outcomes. So this is how we reason about the importance of each features, by observing the manipulations on the attention weights. Then we use this attribution framework and propose a bias mitigation algorithm. So what we do in our algorithm is we first use the classification model to learn the attention weights, similar to how I described in the beginning of this section. Then we loop through all the features existing in the data set, and to reason about the effect of each feature, we use the attribution framework that I just described. So basically, we are zeroing out the attention weight corresponding to the Kate feature. Here, let's say we report the statistical parity difference from when the attention weights are not manipulated. And we see that if the fairness measure is improving, we know that this feature was problematic. So we mark this feature as problematic, and we put it in the unfair feature set. Then for each feature that was marked to be problematic and was put in the unfair feature set, we use a decay rate value, here marked as DR, and we diminish the effect of those problematic features. So now we have a new set of attention weights that we have reduced the effect of those problematic features, and hopefully this is going to give us more fair outcomes, because we have diminished the effect of those features that are contributing to unfairness. Then we perform experiments on both tabular as well as non-tabular or text data. So for tabular data, we use adult data set as well as heritage health data set. In adult data set, the prediction task is whether individuals' income exceeds 50K or not, and we use gender as the sensitive attribute. For a heritage health data set, the prediction task is patient survival rate, and we use age as the sensitive attribute. For the text data, we use the BIOS data set, and the prediction task is given a bio describing a bio of an individual, predict the occupation of the person, and here more specifically, we just consider nurse versus dentist bios. And previous work has shown that this the models trained on these data sets can be biased, in a sense that if a female word appears in the bio, it's more likely for the model to predict the occupation as being nurse, while in reality, maybe the occupation, the bio was representing a bio of a dentist or a doctor. So these are associations that the model learns, and these are wrong and undesirable associations that contribute to unfairness. We in our performed experimental results, we decay the decay rate parameter, and we wanted to see whether our attribution framework first correctly identifies the problematic features, meaning if we improve this decay rate value and diminish more the effect of those problematic features, we are going to see more fair outcomes. And this is going to show us that indeed the attribution framework is doing the correct job, as well as our bias mitigation framework, because if we are increasing this decay rate value, we are obtaining more fair outcomes. So we wanted to see whether attribution framework correctly identifies those features, and moreover, decaying these values are going to give us more fair outcomes. And also we wanted to compare our method against different baselines in how we achieve more fair outcomes compared to the other mitigation strategies. And in our results, we show that indeed both the attribution framework and bias mitigation strategy correctly identify the problematic features and are able to give us more fair outcomes, because if we use this decay value more strongly, we see more fair outcomes in the Pareto curves shown below. And we show that our method is comparable to the state of the art. In the adult case, we are almost the best, and for the heritage health data set, we are the second best model. And more interestingly is the fact that none of these baseline models are interpretable, so they're just black box algorithms to obtain fair models, whereas our algorithm is interpretable in a sense that we know exactly what features were manipulated and by how much to get this particular outcome. Then we perform the experiments on the text data, and we compare our post-processing approach to a pre-processing approach, which basically removes all the gender words or problematic words beforehand and then trains a model, and comparing it to a non-debiased model, which basically trains on the overall data set. And on our results, we show that we obtain more fair outcomes compared to the pre-processing, as well as obviously compared to the non-debiased model. And we also show the accuracy fairness trade-off that I also described in the first work, in a sense that still the non-debiased model has the highest accuracy, but we are still outperforming the pre-processing approach. So there is, again, this trade-off between fairness and accuracy. In the bottom of the slide, I also show qualitative results, and you can see that our post-processing approach obtains better qualitative results. So here we show the bio of a nurse, and as shown, the highlighted tokens captured by our approach highlights tokens such as RN, which is short for registered nurse. So which shows that this method captures important features to predict the occupation nurse, whereas the pre-processing approach doesn't capture that much meaningful information. That might explain why lower accuracy than our case. And more interestingly, if you look at the non-debiased model, it only focuses on gendered words such as she or names to predict the occupation nurse, which is totally undesirable, and this is why we need better solutions to mitigate these types of effects. I also want to highlight a couple of advantages that our method has. So our method is able to provide explanations such that the users exactly know what features and by how much they were manipulated to get the corresponding outcome. In our case, adjustments to attention weights are made post-training, so we only need one round of training. So we are really efficient in production setting. You don't need to retrain your model over and over again. You just train your model once, and then all the manipulations of the attention weights are done post-training. We are also able to achieve different trade-offs by controlling the decay rate value. So if you want more accurate outcome, you can sacrifice fairness, let's say, for accuracy by not improving the decay rate value. Our approach doesn't also need to know the sensitive attributes while training, so it can work with any fairness measure and any sensitive attribute. So you just train your model, not considering anything, and then all these manipulations happen after training, so it can extend to other sensitive attributes and fairness metrics not known while training. We are also scalable for large-scale data sets as well as text data, and we are not just applicable to tabular data sets. So I'm going to do a quick conclusion. So in this presentation, I discussed the concept of trustworthy AI under three components: fairness, robustness, and interpretability. Under fairness, we investigated representational harms or biases in common sense reasoning tasks and resources. We showed the types of different types of harms that exist in these resources, from overgeneralization to disparity in overgeneralization and disparity in frequency. And we showed the effect of these problems from propagating from upstream data sets to downstream models. And lastly, a mitigation algorithm. And under robustness, we proposed attacks that can target fairness of the models. And under interpretability, we propose methods that can achieve fair and interpretable outcomes, which is what is desirable. I also want to highlight some additional resources. So we have this survey on bias and fairness in machine learning that describes different methods and approaches, both in machine learning and NLP, covering various types of biases, various types of fairness metrics or notions, and different work that are trying to achieve more and better, fair and better outcomes. And yeah, with this, I'm gonna conclude the talk. And if you have any questions, just feel free to ask, and I'm happy to take questions.
Thank you so much, Nina, for that really important talk. So now we can go ahead and take some questions. We have about 10 minutes for questions. So we can, does anyone in the room have any questions? Sure. Go ahead.
Thanks for a great talk. So in the first section of your talk, when you were talking about like learning the sentiment of the knowledge, the fact pieces, and adjusting for that after the fact, and it's very important work. I wonder if you're aware of anything that's trying to adjust that at the stage of building the knowledge bases, so not even letting that the things with poor sentiment or the biased facts from entering into the knowledge base. And I don't even know if that's the right question to ask, but I'm just curious about your thoughts.
So these knowledge bases are mostly crowdsourced or are gathered from online sources or forums, and it's not possible to say that, okay, we are not gonna hit some of those cases because we see that some of the forum, like it's inherent to human discussion to impose these biases in the know. So
Yeah,
it's kind of, I don't know how to say, but it's inevitable to not not have these types of issues in the data sets, and this is where the issue of bias in data sources come from. And the only thing we could do is this filtering approach. It still doesn't let the model to see any of that bad data resources, so we are just filtering these data points. Of course, there can be methods that are in processing that are not touching the data, but touching the model, but we wanted to focus on the data. And as you said, we are kind of acting as a filter to filter those data points. But to say that we are gonna never see such cases, it's kind of, in my opinion, not possible, because again, these sources are crowdsourced or crawled from online forums, and we unfortunately see such cases.
makes a lot of sense. Thank you.
Well, I have a question. Nobody else? Okay, I have a question. So so thank you first for the talk. It was really great, and I've learned a lot. I mean, this is very outside my field of research, so that might be a silly question, but my intuition would be that pre-processing, and I'm referring to the third part of your talk, that pre-processing and removing, let's say, the gender information, like removing the she in the text, would potentially improve the accuracy, and we're seeing the reverse. Can you maybe tell us?
Yeah, so this trade-off between fairness and accuracy is something that is totally, like, for people who are working on this is something that is a fact almost, but that's why people are working to improve. And the issue is this strong correlation between these features to some gender-related occupations, and the model learns those easy correlations and which are not desirable, and it obtains higher accuracy, because in reality, yes, maybe there are more female nurses than male, so you might end up getting more accurate outcomes, but then you will end up having this false positive, false negative issues, that there are still cases that there are females and doctors, but the model, because was picking up on these undesired associations, is making undesirable predictions. And this is what exactly we report as in the fairness metric, true positive rate differences. Yeah, accuracy might improve because these are easy associations learned from patterns in the data, but it's not always the best to go with, because obviously it's not true. But yeah, this is a well-known fact in fairness, and it's a really hard question to answer. It's an ongoing research on how to avoid this fairness accuracy trade-off, or there are many theoretical work on why even we have such cases. So if you're interested, I think we also cover some of them in the survey paper as well.
Great, thank you.
Oh, there's a question in the room. Go ahead.
Thank you for the talk, and certainly broaden my horizon on those things. I'm just wondering, you're talking about the bias. I'm just wondering that sometimes in the name of de-biasing, actually you may introduce bias because you want to direct this toward a certain direction on your opinion. This is the bias, that is not bias. Or human, I'm not yours, I'm just saying.
So yeah, that's a really good question. That's why there is still no universal notion of fairness. And in our work, we have, I don't know, for the bias notions, we have more than 20 bias notions. And for fairness notions, we have, I think, over 10 notions, and it's even growing. So because there is no universal notion fairness, it's possible that if you optimize for one notion, you might ruin the other notion, and it's not possible to consider all the aspects. That's why depending on the production setting you are in, depending on the model you are training, who is gonna get affected, that's why people audit these systems first and say, okay, in our use case, considering these outcomes, this fairness notion might be the best, so they go optimize for that. But I agree that doing that might impose other issues, and this is something that is still unclear, because fairness can be subjective, and to some people it might mean something to some other, and this is again an issue that is really important, but unfortunately it's not solvable easily because there is no universal notion for fairness. If it was, we could maybe quantify it or somehow try to obtain more fair results, but because there is no such a thing, we see such problems as well, and I agree.
Are there any questions online? If not, any other questions from the room? Okay, so I think we can end there. Thank you so much for your talk and those amazing questions. And yes, thank you.
Thank you.